Hello, everyone. Welcome back. Today, we are going to be talking about basic probability concepts. Today is our very first day in Unit 3, so hang tight. All right, so what is probability? Probability basically aims to tell us how likely a certain outcome is. So, for example, there's people who suggest that, oh, there's a 30% chance of rain tomorrow, right? That's a probability that we're, basing off of various geographical factors. What else? Um, maybe we want to know how likely it is that we're going to roll a die and get a six, because if we get a six, then we land on the property we want, the monopoly, or something like that as well. Maybe we want to know how likely it is that we're going to flip a heads, heads or tails, so that we can win a bet we made with somebody, or, win some prize, or who knows what, or get to go first on something, whatever it is that we're using the coin to decide, right? So that's basic probability. So I want to talk a bit about certain probability notation, and also probability basic definitions as our first thing, because I think everybody kind of has a basic understanding of what probability means and what it is. I'm sure you've done it before at some point, probably not since middle school, most likely, if you followed the Ontario curriculum all the way through. However, what you might not know is certain definitions that are important to probability and things like that. You may have just been asked, well, do you think this is like something likely or unlikely, and written one of those down, or in some cases maybe given a fraction, but that might be about it up until today. So in probability, the term experiment, like rolling a die, is used to describe a well-defined process from which observations may be made in which distinguishable outcomes or possible results. So for example, let's say we roll a die, let's say that's our experiment, and we want to know how likely the die is to get an even number, or how likely the die is to get a six, right? We have very distinguishable outcomes, right? The outcomes are things like 1, 2, 3, 4, 5, 6. Or if the experiment is flipping a coin, there's two outcomes: either we get heads or tails, and so on. If the experiment is looking outside and seeing what the weather's like today, the outcomes could be snowy, rainy, hailing, sunny, cloudy, etc. Right? Maybe there's more I missed in there, but you get the idea, right? There's different outcomes that we can clearly tell the difference between. I can look outside and I can tell you whether or not it's raining, or if it's snowing or not, or things like that. I can tell that. I can look up at the sky and say either it's cloudy or it's not cloudy, or maybe it's somewhere in between there. But we can look outside and we can tell the difference between these different types of weather. Let's move on. The term sample space is a set of outcomes that is all the possible results of the experiment. So, as we were saying before, with here's the potential outcomes, that's the same as the sample space. So, the sample space, or set of potential outcomes for rolling a die, is we could either roll 1, 2, 3, 4, 5, 6. Just as flipping a coin, what's the sample space? Heads or tails. And that's all. Now, probability is a measure of the likelihood that a certain event will occur, right? So let's say an event. And what's an event? An event is a subset of the outcomes. So that's a subset of the sample space. So, for example, let's say we want to know the probability of rolling a 2. Well, 2 is one of the possible outcomes. We want to know what are the chances that we will roll that 2 and not roll one of the other possible outcomes, right? Or, sometimes something is impossible, right? What are the chances of rolling a 10 on just one die? Well, the chances are zero, because I don't see 10 as one of the possible outcomes at all, right? Or let's say it's heads or tails on our dice, or not on our dice, on our coin, and I want to know what's the probability that we'll get a heads, right? That's something I could figure out. What's the probability that I'll get a tails? Or maybe what's the probability that I'll get either a heads or a tails? Well, that's certain to happen, because those are the only two possibilities. Those are the only two things in our sample space. So one of those things is bound to happen. So it's certain that at least one of those things will happen, right? Or not at least, but exactly one of those things will happen if we choose to flip the coin once as our experiment. So long story short, an experiment is what we do. The sample space is all the possible outcomes or results that could happen from the experiment. And the event is basically what we're measuring, right? What the probability is actually measuring what is the likelihood that something specific, the event, will actually occur. So let's talk about the probability scale for any event A. So there's a scale here that starts from 0 and ends at 1. If the probability is 0 for something, that means the event is impossible, right? That means the event is impossible. Let's say that the probability of something happening is 1. That means the event is certain. I'm going to give some examples of some things that are impossible. It's impossible to roll a 10 on a one sided die that only has 6 sides, where the sides are 1, 2, 3, 4, 5, 6. It's also impossible to flip a paper on a coin, right? Paper isn't one of the options, it's heads or tails, right? Or let's say we're playing rock, paper, scissors. It's impossible to choose anything other than rock, paper, scissors, right? Maybe we're playing a variation where there's more things, but even then, there's only a certain set of things we can choose, and it's impossible to choose something that's outside of that is outside of that while still going in the confines of this game. Now, what about something that's certain to happen? Well, it is certain that if I roll a die, I will get a number, right? If we're asking what's the probability that if I roll a die, I'll get some number, well, 1, right? It's certain to happen. I'll certainly get some number, right? Or even if we just limited it to what are the chances that I will get a number that's either 1, 2, 3, 4, 5, or 6? Well, again, that's also certain. It's definitely going to happen. Or what's the probability I'll get either a heads or a tails? So that when I flip my coin, it'll be one of those two things. Well, that's certain, right? The only choices are heads or tails, so it's got to be one of those things. There's no third outcome, there's no third side on our coin, right? And so that's important to keep in mind. Now, reality is it's the numbers between the numbers that matter most, because most things will not be either impossible or certain. These are the extremes of the probability scale. Most things will have some probability that makes them closer to impossible or closer to certain, but not exactly impossible or exactly certain. So for example, if we have a probability of 0.5, that means it's equally likely to happen or not happen. So it might happen or not. What if we have 0.25? Well, it's possible, but unlikely, right? There's only a 1 in 4 chance here. So possible, but unlikely. What about 0.75? Well, that's going to be possible and likely. I'm not going to say possible and certain because it's not certain, right? There's still a 1/4 chance or a 0.25 chance of it not happening, right? But basically, this is our scale that goes from 0 up to 1. And the closer we are to 0, the more likely it is to not happen, for the event to not occur and not be the outcome. And the closer we are to 1, the more certain we are, right? The more likely it's going to be. However, it's not completely impossible unless the probability is exactly 0, and it's not completely certain unless the probability is exactly 1, right? We could have a probability really, really close to 1 that's 0.98, right? 98%. And that would be very, very close to certain, but still not completely certain because it's not quite at that 1. So that's the main thing to keep in mind, that we could have anything from impossible to certain, and it must be between 0 and 1. Now keep in mind all probabilities must be between 0 and 1, inclusive of 0 and 1. Anytime we get a probability number that is not, that is a problem, right? Because that cannot be the true probability. Now if it's a percentage, that's okay, because a percentage is just over 100, so that's totally fine. Or if it's a fraction, then that's fine as long as the fraction is between 0 and 1. However, the actual probability that we get cannot be less than 0, and it cannot be greater than 1. Right? 0 is the extreme on the left, and 1 is the extreme on the right, and that's that. Let's talk about notation and formulas. So n with the brackets a here, this notation right here, is the number of outcomes where a happens. N with the S is the number of total outcomes, right? So for example, let's do our die example for instance. Let's say we want to know what are the number of outcomes on the die where we'll get an even number. Well, there's 3 of them, right? So n with the brackets and a will be 3 because there's 3 possible outcomes. Now, the total number of the outcomes, the number of items in our sample space, this one here, this would be 6 because there's 6 total possibilities in our sample space for this experiment, right? So that would be 6. What about P of A, right? Probability of A is the probability that event A occurs. So that's where we're going to put the number of outcomes where A does happen over the total number of outcomes to see, okay, how likely is this to happen? If there's only one chance out of 6 chances that something will happen, then that's not that great a chance. But if there's 4 or 5 chances out of 6 that something will happen, then it's relatively likely to happen, right? Now, these two notations, A prime or not A, are the number of outcomes where A does not happen. So this is the opposite of where A does happen. It's all the cases where A does not happen, right? Then we have probability of A naught or a probability of A prime, and that is going to be the number of cases where that event does not happen over the total number or the sample space. Or indirectly, we could also say that the probability of A not happening is equal to 1, right, minus the probability of A happening, right? Because 1 is the total number of all the cases. And if we subtract off the times where A does happen, we're left with the probability if we subtract off the probability that A does occur, then what are we left with? The rest of that, the probability scale where A does not occur, right? Good. So this notation formula part is very, very important. So I do recommend writing this down. It's very, very key information that you will see consistently brought up throughout this probability unit and possibly even a little bit in future units, especially P of A. This you'll see quite often. And this is actually, for this reason, this is why I don't like when, P and then bracket something means something else like profit or other things, because it reminds me too much of probability, right? It looks the same as probability, even though there are other in other branches of math, there are technically things, other than this. Good, very good. So let's do an example. Here it says there are 12 females and 8 males in a math class. If a student is randomly picked from the class, what is the probability that the student is a female or a male? Okay, so let's see. Well, first question I need to ask is we want the probability of what? Probability of a female if we randomly select one person. Now, how many females are there? What is the number of females here? There's 12. And what is the total number of all students? Well, that would be the 12 females plus the 8 male students is 20 students in total. So that means the probability is 12 over 20, which is the same as 3 over 5. So that's our probability, 3 over 5, or about 0.6 if we wanted to put it in decimal form. So it seems like it's slightly more likely. 0.6 is a bit closer to 1 than it is to 0. So that suggests to us that we're slightly more likely to choose a female if we randomly select, which makes sense because there are more females in this classroom. Now, what's the probability we'll select a male? So there's actually two ways we could solve this. We could either solve this directly and say probability of a male is going to be 8 over 20, which is 0.4, right? Because there's 8 males and there's 20 students total. Or another way we could solve this is we could say probability of male is going to be 1 subtracted from probability of female, because that's the only other option in this situation, right? So we have 1 minus 0.6, which is equal to 0.4. So either one of these ways is perfectly fine, perfectly valid. I wouldn't have said that one or the other is necessarily more efficient because, they're both only a couple of lines long. So whichever one you prefer is totally fine. Okay. Let's do a few more examples. Let's move to example 2. Example 2 says a number between 1 and 25 is chosen randomly. What is the probability that the number is odd, less than 14, or a multiple of 4? So let's start with A. What's the probability the number is odd? Okay, so let's start with the total number of outcomes. There's 25 total outcomes. Now the question is, how many of those outcomes are odd? Well, let's see. 1 is odd, 3, 5, 7, 9, etc., all the way to 25. And so just over half of them, which is 13, of these are odd numbers. So therefore there's 13 odd numbers possible over 25 total numbers possible, right? And so 13 over 25 is our answer. How about less than 14? Well, probability of less than 14 would be equal to anything from 1 to 13. So there's 13 possibilities here over the total number of possibilities, which is 25. So actually, probability of the number being odd is actually the same as the probability of the number being less than 14, because in either case, there's 13 numbers that do fit, that do satisfy that event, that do satisfy the requirements, and there's the other ones do not. The other 12 don't. How about C? C is probability of a multiple of 4, right? Multiple of 4. So how many of these numbers are multiples of 4? Well, let's see. 4 is 8, 12, 16, 20, and 24. So there's 6 multiples of 4 here. Out of the total number of outcomes in all is going to be 25. So the probability that we choose a multiple of 4 randomly is 6 divided by 25. Okay, very good. Let's move on to example 3. Example 3 says, if there are 9 colored marbles placed in a dark bag, 5 red, 3 white, and 1 blue, if you reach into the bag and select a number, what is the probability the marble is blank? Okay, I assume they mean select a marble, not select a number. It says select a number here, but I assume they mean marble. That would make a lot more sense. What is the probability that the marble is red? Well, let's see. Probability of red is equal to, well, let's see, there's 5 red marbles, so 5 is the number of outcomes that fulfill this event of it being red, and in total there's 9. So 5 over 9 is the answer. Now we could ask, what is the probability that it is white or blue? Well, there's 2 ways to do this. One way is we could say, well, there's 3 white marbles and 1 blue marble, so that's 4 marbles total over 9. So that's a way we could figure it out. Another way we could figure it out is we could say, well, it being red or blue is the opposite of it being red, right? There's no other colors. It's either red or it could be white or blue. So we could say 1 subtracted, if we do 1 minus 5 over 9, we get 4 over 9 that way. And that's also a perfectly valid way to do it. But either way, the answer is 4 over 9. So we're actually more likely to choose a red marble than we are to choose either a white or a blue marble. Or, even if we combine those two and put them in one category, we're still more likely to get a red marble because the red marbles outnumber all other marbles. Very good. More than half of the marbles in that bag are red. Okay, let's move on to example 4. So example 4 says what? Example 4 says, if 2 six-sided dice are rolled, draw a tree diagram to show all possible outcomes. So we actually haven't ever drawn a tree diagram before, so I'm going to draw one right now and show what I mean by that. So basically, let's start with the first die. What are the possibilities for the first die? Well, the first die could either be 1, 2, 3, 4, 5, or 6, right? 1, 2, 3, 4, 5, 6, right? And what about the second die? It could be either 1, 2, 3, 4, 5, 6, or maybe we got a 2 and we also got 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. This is not the best looking tree diagram, but that's okay. 1, 2, 3, 4, 5, 6. 4 could be 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 5 could be 1, 2, 3, 4, 5, 6. Or 6 could be 1, 2, 3, 4, 5, 6. Amazing. All right. Well, there we go. Awesome. Okay. So, that's not the nicest looking tree diagram, but there you go. You get the idea that either we roll a 1 first, end of 1 second, 1 first, and then 2, 1 and then 3, 1 and then 4, 1 and then 5, 1 and then 6, Or maybe we rolled a 2, then 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6, and so on, all the way till we get to number 6 rolling first and then rolling the other ones. Here it asks, what is the probability that the sum of the rolls is 7? Okay, so first things first, we need to know what are the total number of rolls we could have here. Well, let's go back to our combinations and permutations unit for a minute. Well, the thing is, the number of outcomes possible, so total number of outcomes, oh, total does not have two L's, total number of outcomes would be what? Well, that would be how many outcomes are there for the first part, for the first stage? Well, there's going to be 6. We could either get 1, 2, 3, 4, 5, 6 the first time. And then how about the second time? Same thing. We could get 1, 2, 3, 4, 5, 6 on our second die. So our total number of possible outcomes is 36 if we just apply that knowledge from combinations, permutations. That was actually taught in the very first lesson of the last unit of unit 2. So if that is confusing, definitely go watch that one, and it will help you out with understanding that why the total number of outcomes here must be 36. And now we want to know what is the probability that the sum of the rolls is 7. So if we take the two numbers and we add them up, we get 7. Well, let's count that. Either we could have a 1 and a 6, and that would make 7, or we could have a 2 and a 5, that would make 7. Or we could have a 3 and a 4, that would make 7. Or we could have a 4 and then a 3, that would make 7. Or we could have a 5 and then a 2, that would make 7. Or we could have a 6 and a 1, and that would make 7. So all of these would make a 7. So that means that the probability of rolling a 7 is equal to 6, right? Because there's 6 possible outcomes here, divided by 36, right? Because 36 is the total number of outcomes here. And that is going to simplify to 1 over 6. So there's a 1 in 6 chance of rolling a 7. So not that likely. However, fun fact, 7 is actually the most likely roll you can get as compared to any other roll individually. But of course, if we're talking about are you more likely to roll a 7 or a non-7, well, you're more likely to roll a non-7 if we're just going to lump every other number that you could possibly get all together into one group. Okay, so let's try part C. Part C asks, what is the probability that the sum of the rolls is greater than 8? Okay, well, let's think about that. We need to know how likely that really is to occur. So let's think about this. There's two ways we could approach this. We could either say, well, let's, write out all the different ways that this could possibly happen, that we could get something that's 8 or greater than 8. Or there's another way we could think about this, which has to do with this whole thing being symmetrical. We could actually recognize this is symmetrical, and we could say, well, it must be 15 over 36 for that reason. Now that said, I'm not going to expect that level of knowledge just yet, as we've only started this unit. So I'm going to show in full detail the first way. But if it did pop into your head right away of 15 over 36, that's totally fine too. In fact, that's really good if you thought right away that must be our answer. Very good. Okay. All right. So let's do it. So if we want a sum of rolls that is greater than 8, greater than 8. I thought it was greater than or equal to 8. Okay, so actually scratch the 15 over 36. That wouldn't quite be right. That means it's either 9, 10, 11, or 12. So let's write the number of ways for 9. So we could have 4 and 5, or 5 and 4, 3 and 6, or 6 and 3. So there's 4 ways for that one, right? 4. And then for 10, it could be 5 and 5, or 6 and 4, or 4 and 6, so that's 3. And then we have 11, which is 5 and 6, or 6 and 5, which is 2. Or 12, which is just 6 and 6, so that's only one way. So if we add up all those ways, that is going to be 10. 10 ways total. So the probability of greater than 8 is equal to 10 over 36, which is going to be 5 over 18. So that's going to be our answer for our probability. So we're quite a bit more likely actually to get something that's 8 or less than we are to get something that's greater than 8. There just aren't that many ways. And keep in mind that almost half of those ways come from 9 itself, right? We're more likely to get 9 than any of these other individual numbers if we are to roll something that is greater than 8. Very good. All right. Well, we're going to talk about odds and probability versus odds in the next time. But that is it for our first lesson today, and I will see everybody back for lesson 2. Bye, everyone.